Okay, so we're going to go over section 9.10 and we're going to talk about Maclaurin and Taylor series. So in the last section, 9.9, we went over how to find the power series representation of a function using the formula for the sum of a geometric series. And then we used integration and differentiation and different things to find other power series. And so today we're going to go back to Taylor and Maclaurin and come up with series representations for functions. And so if a function f has derivatives of all orders at x equals c, then the series, whose terms are given to you by the nth derivative evaluated at c divided by n factorial times x minus c to the n, which is just f of c plus f prime of c times x minus c plus dot 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 plus the nth derivative evaluated at c divided by n factorial times x minus c. But rather than stopping like we did for the polynomials, this is an infinite polynomial and it just goes on forever and ever. And this is called a Taylor series for f at c. Moreover, if c equals 0, then the series is the Maclaurin series for f. So when c is 0, what you have is the Maclaurin series. Now, we came up with the series in the last section, but this theorem here tells us that no matter how you come up with the series, the coefficients of the series are given to you by the formula that we used for the Taylor and Maclaurin series. And so it doesn't matter how you come up with it, the coefficients are going to be the same. Theorem 9.22, the form of a convergent power series. If f is represented by a power series, f of x equals the summation of a sub n times x minus c to the n for all x in an open interval I containing c, then your terms are given to you by the formula the nth derivative evaluated at c divided by n factorial. And f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c factorial, times x minus c squared plus dot dot dot. You need to be careful with this. If f is represented by a power series, then this is what the series looks like. It does not tell you that if you have a power series that converges, it converges to the function. So that's this remark here. It's very important. Be sure that you understand theorem 9.22. The theorem says that if a power series converges to f of x, then the series must be a Taylor series. The theorem does not say that every series formed with the Taylor coefficients will converge to f of x. Okay, so finding a Taylor series. In exercises 5 through 16, use the definition of the Taylor series to find the Taylor series centered at c for the function. Okay, so we did something similar to this in the last section. We didn't use the Taylor formula. We just used the geometric series and made appropriate substitutions. And what you're going to see is that you're going to get the same thing, right? So to use the Taylor formula, this is just like we did before, except instead of stopping at 4 or 6 or 8, we're going to go on forever. But we can't go on forever, so we're just going to go long enough until we see a pattern. All right, so this is the table that I was making before. N, the nth derivative evaluated at x, and then the nth derivative evaluated at 2. And then that will give you your an. Sorry, what did they call it? So your Cn, I think we had called it Cn. And your coefficients are given to you by evaluating your nth derivative at 2 and dividing by n factorial. And so again, when n is 0, then it's just the original function, which, to make it easier to differentiate, we are going to write 1 minus x raised to the negative 1. When you evaluate this at 2, you get the inside becomes 1, and 1 to any power is 1. And so then your C naught is 1. And so then when n is 1, then you bring down the exponent, negative 1, times 1 minus x, take 1 away from the exponent, negative 2, times the derivative of the inside, but the derivative of the inside is 1, so you just get 1. When you put in 2 to 2 minus 1 minus 2, oh, I'm sorry, I did this wrong. 1 minus 2 is negative 1, and negative 1 to the negative 1 power is negative 1. And so now here it is negative 1 to the negative 2, and that is 1. And so then C1 is positive 1, C naught is negative 1. And when n is 2, then you're going to bring down the exponent, negative 2, take 1 away from the exponent, negative 3. Same inside, times the derivative of the inside, and so now you get a positive 2. When you plug in the 2, 1 minus 2 is negative 1, but negative 1 to the negative 3 power is negative 1. And so then you get negative 2. But then for C2, you're going to take your negative 2 and divide it by 2 factorial, which is just going to be negative 1. When n is 3, then you're going to take the third derivative, so this is going to be negative 6 times 1 minus x to the negative 4 times the derivative of the inside, which is negative 1. And so then here, when you plug in the 2, you are going to get negative 1 to the negative 4, which is positive 1. And then you will get 6. And so then your C3 will be 6. Over 3 factorial, but 3 factorial is 6, so your answer is 1. When n is 4, and you're going to bring down the negative 4, and you're going to get negative 24, 1 minus x to the negative 5, and times the derivative of the inside, which makes that a positive 24. And then when you put in the 2, 1 minus 2 is negative 1 to the negative 5 is negative 1 times the 24 is negative 24. And when you divide that, so then C4 is negative 24 divided by 4 factorial. 4 factorial is 24, and so then you get negative 1. And what you can see is that it's very obvious that the pattern is, right? Because when you're going to bring this down, you're going to end up with 120, which is 5 factorial. And then this is 1 minus x to the negative 5 times the derivative of the inside. This should have been negative 5 factorial. So then you end up with positive 5 factorial. And so then this is going to be positive 5 factorial. And then your C5 is going to be 1. And so then your Taylor series, you can see, is just going to be negative 1 plus x minus 2 minus x minus 2 squared plus x minus 2 cubed, and so on. We could write this in series notation. You can see that you have an alternating, so it's negative 1 raised to the n plus 1 because we're going to start at 0. And we're going to go out to infinity. And then you have x minus 2 to the n. And you can see that this is just a geometric series. And so then the first term is negative 1 over 1 minus the common ratio, but the common ratio is x minus 2. And so then this becomes negative 1 over 1 minus x. And so this tells us that we could have gotten there from the geometric series formula. Oh, I'm sorry, I made a mistake here. The common ratio is not x minus 2. The common ratio is negative 1 times x minus 2. And so then that would then be, let me go ahead and get rid of this. So then that would make this negative 1 over 1 plus x minus 2, which would then be the negative 1 over x minus 1. And if we multiply the top and bottom by negative 1, we get 1 over 1 minus x. And but that just basically tells us that we could have gotten here from the techniques that we did last section. We would have got the same answer. And so, but by recognizing that this is geometric, the other thing we want to do with these series is find the interval of convergence. Your common ratio is 2 minus x, and so then 2 minus x needs to be between negative 1 and 1, and so then if we subtract 3 from both sides, we'll get, 2 from both sides, we'll get negative 3 is less than negative x, which is less than negative 1. Multiply both sides by negative 1, and you'll get 3 is bigger than x, which is bigger than 1. So your interval of convergence here is from 1 to 3. And that's your interval of convergence. No need to use the ratio test here. This is a geometric series, and so then you can get the interval of convergence because your common ratio needs to be between negative 1 and 1. Okay. So find the Maclaurin series for y equals e to the x. So again, Maclaurin series, we have n, fn of x, fn of 0, and then cn. When n is 0, that's your original function, e to the x. When you plug in 0, you get 1, and so then c naught is 1. When n is 1, the first derivative is e to the x. Then your first derivative evaluated at 0 is still 1, and so then c1 is 1. When n is 2, your derivative is still e to the x, you still get 1, and over here you get c2 is 1 over 2 factorial. When n is 3, still your derivative is still e to the x. You put in 0, you still get 1, and then you get 1 over 3 factorial. And from there it's pretty clear what's going to happen. So then this series, the Taylor series for e to the x, is 1 plus x plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. In summation notation, this is the summation from n equals 0 to infinity of x to the n over n factorial. Right? So for the interval of convergence, we can take the limit as n goes off to infinity of the absolute value of x to the n plus 1 divided by n factorial, n plus 1 factorial, multiplied by the n factorial over the absolute value of x, which is then the limit as n goes off to infinity of, if we clean that up, we end up with just the absolute value of x over n plus 1, and this is 0, which is less than 1, therefore converges for all x. So the Maclaurin series converges for all x, but again, up to this point right now, we do not know that it converges to e to the x, so you need to be careful with that. Find the Maclaurin series for y equals sine of x. You should do these on your own. Pause the video. N fn of x. Maclaurin, it's always fn of 0. We're always doing this at 0 for Maclaurin. And your Cn, which is again your fn evaluated at 0 divided by n factorial. When n is 0, we're dealing with the original function, sine of x. Sine of 0 is 0, and so then C naught is 0. When n is 1, the derivative is the cosine of x. When you're evaluated at 0, you get 1, and so then C1 is 1. When n is 2, you get the negative sine of x. When you plug in the negative sine of x, you get 0, and then the C2 is going to be 0. When n is 3, you get the negative cosine of x. Evaluated at 0, you get negative 1, and then your C3 will be negative 1 over 3 factorial. And when n is 4, you end up right back where you started. You still get 0, and so then your C4 is 0. And then you're going to just keep repeating for these numbers, 0, 1, 0, negative 1, 0, but your Cn is always over n factorial, so you're always going to have an n factorial. So your Maclaurin series for the sine of x looks like this: x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. We can write this in summation notation. We can start this at 1. We can start this at 1, and so we go from k equals 1 to infinity, and x to the exponent is 1, 3, 5, 7. Those are just the odds. 2k minus 1. And whatever the exponent was, that was the same factorial that was on the bottom, 2k minus 1 factorial. And it alternates positive, negative, positive, negative. So we have this factor of -1, and it starts out positive, and we're starting at 1, so we should go k plus 1. And that is the series for the sine of x, right? And again, we should look at what is the interval of convergence for this series. And again, we do that with the ratio test. And so we apply the ratio test to see what your interval of convergence is. And so then we're going to take the limit as k goes off to infinity. Again, you're going to get a lot more out of this if you try this on your own and then compare your work to mine. And you're going to take the limit as k goes off to infinity of, when we put in k plus 1 for n, we'll get 2k plus 1. Don't forget the absolute values on the x. And in the denominator, you'll get 2k plus 1 factorial times the reciprocal, 2k minus 1 factorial goes on top, and x to the 2k absolute value, 2k minus 1 goes on the bottom. Here we subtract the exponents. Sorry about that. Here we subtract the exponents, and 2k plus 1 minus 2k minus 1, we end up with an exponent of 2. And on the 2k minus 1 factorial over the 2k plus 1 factorial, we're going to get a factor of 2k plus 1, a factor of 2k, and then when we get the factor of 2k minus 1, it goes away. And so this is what we get. The top is staying fixed. Once we fix x, the top is staying fixed, and the bottom k is going off to infinity, so it's increasing without bound. The answer is 0, which is less than 1. Therefore, converges for all x. And the interval of convergence is from negative infinity to infinity. But again, this doesn't mean that it converges to the cosine of x. We'll get there in a little bit. We just have a series that we know converges for all x's. Find them. Before we go on here, let's come back to over here. Something I forgot to mention. When you were dealing with the in trigonometry and you're looking at the sine function, the sine function starts at 0, goes up, comes back down, and then over here goes like this. That's not a very pretty picture, but what we said in trigonometry was that the sine function was odd. And notice that all of your exponents are odd, right? Now let's go on to the cosine function. It's going to be very similar. N fn of x, fn of 0, because it's Maclaurin, and Cn, and your Cn is Fn of 0 divided by n factorial. And at 0, we get the cosine of x. Evaluate that at 0, we get 1, and so then C naught is 1. When n is 1, you get the negative sine of x. Put in the 0, you get 0, and so then your C1 is 0. When n is 2, you get the negative cosine of x. You can plug in the -1, and you get, you plug in the 0, you get the -1. And then your C2 is -1 over 2 factorial. When n is 3, you get it back, you get the sine of x. Sine of 0 is 0, And so then your C3 is 0. And when n is 4, you end up back at the beginning, cosine of x, and then plug in 0, you get 1. And so then your C4 is positive 1 over 4 factorial. For 5, you get the negative sine of x, 0, and then C5 is 0. And you see this is just going to continue. And you can see that then the Maclaurin series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And it's going to be minus x to the 6th over 6 factorial. It's just going to continue on and on and on. We can write this in summation notation. This is the summation from k equals 0 to infinity. And you can see that every time it's just x to the 2k, those are the evens, divided by 2k factorial, right? And you can then find the interval of convergence. So you have the summation from k equals 0 to infinity of x to the 2k over 2k factorial. And so then for the interval of convergence, you're going to use the ratio test, take the limit as k goes off to infinity of x to the 2k plus 2 all over 2k plus 2 factorial times the 2k factorial divided by x to the 2k, and don't forget the absolute value on the x. Again, this cleans up to the limit as k goes off to infinity. When you subtract the exponents, you get the absolute value of x squared. When you break off factors from the factorials, you get 2k plus 2, and then 2k plus 1. And then when you get to 2k, the 2k factorials will go away. So this is what you get. The bottom is growing without bound. The top is staying fixed at the absolute value of x squared. So this is 0, which is less than 1. Therefore converges for all x. And the interval of convergence is from negative infinity to infinity. So again, just because this series converges does not mean that it converges to the cosine of x. We'll get there in just a little bit. So find the Maclaurin series for 1 over 1 minus x. Again, we did this last time using the geometric formula, and we'll do it this time using the definition, and the theorem tells us that it needs to be the same. So n fn of x, fn evaluated at 0, and then cn. And so when n is 0, you have 1 over 1 minus x, and when you plug in 0, you get 1. And so then your C naught is 1. When you have 1, so again we should write this as 1 minus x to the negative 1. We're going to bring down the negative 1 times 1 minus x to the negative 2 times the derivative of the inside. The derivative of the inside is negative 1, so we get a positive. And then when we plug in 0, you get 1 to a power, which is still just 1. And so then C1 is also 1. When n is 2, now bring down the exponent, you get a negative 2. 1 minus x to the negative 3 times the derivative of the inside. But the derivative of the inside is negative 1, so that makes that a positive 2. Plug in 1, you get 2. And then your C2 is 2 divided by 2 factorial, which is 1. When n is 3, you're going to get negative 6 times 1 minus x to the negative 4 times the derivative of the inside, which makes that a positive 6. So this is 6, which is the same thing as 3 factorial. You can see that you're just going to keep bringing down these exponents and you're going to keep getting the factorials. So then C3 is 6 divided by 3 factorial, which is also 1. And then when n is 4, you're going to get negative 24 times 1 minus x to the negative 5 times the derivative of the inside, which makes that a positive 24. Plug in 0. 1 minus 0 is 1. 1 to any power is 1. And you get 24. And so then C4 is 24 divided by 4 factorial, which is 1. At this point, you should realize that you're just going to keep getting 1. So then your Maclaurin series for 1 over 1 minus x is 1 plus x squared plus x cubed plus dot dot dot. You could write that in summation notation as the summation from k equals 0 to infinity of x to the k. And for the interval of convergence here, this is a geometric series. The common ratio is x, and it will only converge when x is between negative 1 and 1. And this is the geometric series that we got for this function, and just by substitution into the formula for the sum of a geometric series, it's the same one. The theorem guarantees us that the coefficients will be the same. So find the Taylor series for the natural log of x about x equals 1. The natural log of 0 is not defined, and so then we can't find a Maclaurin series. So we have to evaluate it at some other nice number, and the natural log of 1 is 0, and that's about as nice as that gets. So we do this about x equals 1. Taylor series. Okay, so n fn of x, fn of 0, cn. Again, you should be doing this on your own, and then making sure that your work and my work matches. When n is 0, you're dealing with the original function, the natural log of, here I put 0, that's not right. The Taylor series about x equals 1. And so then we get the natural log of 1, which is 0. And so then C naught is 0. When n is 1, the derivative is 1 over x, which we will write as x to the negative 1. Make it easier to differentiate. When we plug in 1, we get 1. And so then C1 is 1. When n is 2, now we bring down the exponent, take 1 away from the exponent, plug in 1, 1 to any power is 1, negative 1, and so then you get negative 1 over 2 factorial, which is negative 1 over 2. When n is 3, bring down the exponent, you get a positive 2, x to the negative 3. Plug in the 1, you get 2. So then your C3 is 2 divided by 3 factorial, which is 1/3. 2 over 6, 1/3. When n is 4, Negative 3 times 2 is negative 6. X to the negative 4. Plug in the 1, you get negative 6. Notice that we're not getting 4 factorial, we're getting 1 less than that factorial. We're getting 3 factorial. So then C4 is going to be the negative 6 over 4 factorial, which the 6 is 3 factorial over the 4 factorial, and you're just going to get negative 1/4. And his 5 you're going to get positive 24, x to the negative 5. Plug in the 1, you're going to get 24. 24 is 4 factorial. And so then C5 is 4 factorial over 5 factorial, which is 1/5. And the pattern is pretty clear there. Again, you're not a polynomial in x, it's a polynomial in x minus 1. The constant term is 0. But then your first term is 1 times x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, and then plus x minus 1 to the 5th over 5. To write this in summation notation, we're going to start at 1. X minus 1, the powers are 1, 2, 3, so it's 3. Whatever the power is, that's the same as the denominator. Sorry, that was wrong. 1, 2, 3, so whatever, so that's just k. Whatever the power is, that's what the denominator is, so that's a k. And it's alternating positive, negative, positive, negative. So then we have this factor of negative 1 to the k plus 1, or k minus 1, makes no difference. And there we go. So now let's look at the interval of convergence for this series. So we have the summation from k equals 1 to infinity of negative 1 to the k plus 1 x minus 1 to the k all divided by k. Right? And so then for the interval of convergence, we want to take the limit as k goes off to infinity of, when we absolute value, this factor goes away. And so we don't have that factor. It's because the absolute value of negative 1 is 1. The absolute value of positive 1 is 1. So when we absolute value, that factor goes away. And you just get the absolute value of x minus 1 to the k plus 1 all over k plus 1. And you're multiplying that by k over the absolute value of x minus 1 to the k. Then this becomes the limit as k goes off to infinity. Subtracting the exponents, you end up with x minus 1 over, times k over k plus 1. Again, you need to be comfortable with these results, that when you're looking at a rational expression where the degrees are the same, the limit will be the leading coefficient of the numerator over the leading coefficient of the denominator. And so the k over k plus 1 goes to 1, so this just becomes the absolute value of x minus 1. And so then converges for the absolute value of x minus 1 is less than 1, which implies that negative 1 needs to be less than x minus 1, which needs to be less than 1, which implies that 0 needs to be less than x, which needs to be less than 2. But it does not tell us what happens at 0 or 2, because at 0 or 2, the limit will be 1, and the ratio test is inconclusive at 1. So we have to check those separately. And so to check those, we go in and we substitute in 0 in for x, and we end up with this series, summation from k equals 1 to infinity of negative 1 to the k plus 1 times negative 1 to the k, all divided by k. Now this becomes the summation from k equals 1 to infinity. Same base, we add the exponents, we get negative 1 to the 2k plus 1, and 2k plus 1 is always odd. And since that's always odd, this doesn't alternate. This stays a negative 1. So this is negative 1 times the summation of 1 over k, which diverges because it's the harmonic series, P series, harmonic series. Now, if x is equal to 2, then we get this series of x. We put in 2 there. 2 minus 1 is 1. 1 to any power is 1. We end up with negative 1 to the k plus 1 over k. And this converges by alternating series test. And so then the interval of convergence is from negative 1, from 0 to 2. And we've just figured out that at 0 it diverges and at 2 it converges. So not including the 0 and including the 2. That is the interval of convergence. Okay. Now, here we have this strange function that's defined by in pieces. F of x will be negative 1 when x is less than negative pi over 2. It will be the sine of x in between negative pi over 2 and pi over 2. And it'll be 1 when x is bigger than pi over 2. You have here the graph of this function. And if we go and we try to find the Taylor series for this, the Maclaurin series for this, this is going to have the same Maclaurin series as the regular sine of x, because the only place we're evaluating our derivatives is at 0, and at 0 it has the same formula. But then that tells me then that that Maclaurin series that we get will not converge to this actual function. So again, the point of this example is just because your derivatives converge at one point, at one input, doesn't mean that your series that you made will converge to the actual function. Now, it turns out that if a function f is differentiable through n plus 1, and that previous function that I had is not differentiable through order n plus 1, it stops being differentiable after the first derivative, I believe. In an interval I containing c, then for each x and I there exists a z between x and z, such that your f of x is your Pn of x. So this right here is just your Pn of x plus some error. And it turns out that your error is approximated by this formula. And so then what that means then is if this part right here goes to 0, then your error goes to 0, and your function converges to your, your power series converges to your function. And that's what this theorem tells you. If the limit as n goes off to infinity of Rn equals 0 for all x in an interval, then the Taylor series f converges and equals f of x. So we're not going to go through and prove any of these. We're just going to accept that using this theorem and going through this analysis, all our series that we've just gone over actually do converge to their originating functions. And so then that allows us to write this table, right? And so then 1 over x is the same thing as its Taylor series, sorry, as its Maclaurin series, no, Taylor series right here on the interval from 0 to 2. 1 over 1 plus x is the same as its Maclaurin series on the interval from -1 to 1. The natural log of x is the same as its the natural log of x is the same as its Maclaurin series on the interval from 0 to 2, and so on and so forth. And so what we're going to do now is we're going to use these known series to find new series. And that's what we'll go into now. So in exercises 27 through 40, find the Maclaurin series for the function. Use a table of power series for elementary functions on page 64. That's the previous table. So we already know that e to the x is the same thing as 1 plus x squared over 2 plus x cubed over 3 factorial plus dot dot dot, which can be written in summation notation as the summation from k equals 0 to infinity of x to the k over k factorial for all x. So then it should make sense that if all I've done is replace the x with negative x over 3, then e to the negative x over 3 should be the same thing as replacing the x with the negative x over 3 over here. So this will be 1 plus negative x over 3 plus negative x over 3 squared over 2 plus negative x over 3 cubed over 3 factorial plus dot dot dot. And to write it in summation notation, there's no need to do anything other than go to the one that's written in summation notation and replace the x with with negative x over 3. So in summation notation, this would be the summation from k equals 0 to infinity of negative x over 3 raised to the k, all divided by k factorial. And if we wanted to expand that a little bit, we could. This is the summation from k equals 0 to infinity. The negative 1 will go to the k, the x will go to the k, and the 3 will go to the bottom, raised to the k, and then we still have the k factorial on the bottom. The interval of convergence is for all x, because because this converged for all x. IOC is from negative infinity to infinity because the original series converged for every possible real number. So we already know that the natural log of x, the natural log of x can be rewritten as, let's come back over here, the natural log of x is x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 plus dot dot dot, which we can write in summation notation as the summation from k equals 1 to infinity of negative 1 to the k plus 1 negative 1 to the k plus 1 times x minus 1 to the k, all divided by k. And all we've done is we've just replaced the x with 1 plus x cubed. So then the natural log of 1 plus x cubed, we just go and we replace the x with 1 plus x cubed. And when we plug the 1 plus x cubed there, the 1's go away and we get x cubed minus x cubed squared, x to the 6th over 2, plus x cubed to the 3rd over 3, and so on. If we wanted to write that in summation notation, we can simply go to our summation notation, summation from k equals 1 to infinity, and replace the x minus the x with the 1 plus x cubed, which will then, we still have the factor of negative 1 to the k plus 1, the x 1 plus x cubed minus 1, which is going to be x cubed to the k, and then over here you have k. So we can clean this up. Summation from k equals 1 to infinity of negative 1 to the k plus 1, and then x to the 3k, all divided by k. For the interval of convergence, there is absolutely no need to use the ratio test. We know that for the natural log, whatever you put in, which is 1 plus x cubed, it will converge as long as your whatever you put in is between 0 and 2. And so now if we subtract 1 from both sides, we get negative 1 is less than x cubed, which is less than 1. And if we cube root all three sides, then we get negative 1 is less than x, which is less than 1. And so your interval of convergence is from negative 1 to 1. Oh, I'm sorry, this was a strict inequality. I'm sorry, this was not a strict inequality. And so then it will converge at 1. Now, your problems here do not ask for the interval of convergence, but I expect to see the interval of convergence because it's implied. A power series is useless without knowing what numbers you can substitute into it. So you need to give the interval of convergence, and here's how you can find it. The sine of x, we already know, was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot, which in summation notation is the summation from k equals 1 to infinity of negative 1 for the alternating 2k, I'm sorry, k plus 1 to start positive, x to the 2k minus 1 to get the odds, and divided by 2k minus 1 factorial. So the sine of x cubed all you've done is replace the x with x cubed. So you just replace the x with x cubed there, and you will get x cubed minus x to the 9th over 3 factorial plus x to the 15th over 5 factorial minus x to the 21 over 7 factorial plus dot dot dot. In summation notation, you could have just plugged it into here. That's substituting in the x cubed in for x is not going to change that -1 to the k plus 1. It's still summation from k equals 1 to infinity. And then all you're doing is replacing the x with x cubed. So this becomes x cubed to the 2k minus 1. So this becomes 6k minus 3. You multiply the exponents, and 3 times 2k minus 1 is 6k minus 3. Okay. And then on the bottom, that didn't change at all. It's still 2k minus 1 factorial. But we wanted the formula for 2 times the sine of x cubed. So if we multiply both sides of this formula right here by 2, and then we end up with 2 times the sine of x cubed is equal to 2x cubed minus 2x to the 9th over 3 factorial minus 2 times x to the 21 over 7 factorial, and so on. And in summation notation, it's the same formula, except now you have an extra factor of 2. You still have the factor of -1 to the k plus 1, and now you have a 2x to the 6k minus 3, all divided by 2k minus 1 factorial. And your interval of convergence, don't forget that. This converged for all real numbers. No matter what real number you put in for x, this will converge. So then this will converge for all real numbers as well. Negative infinity to infinity. Okay, in exercises 47 through 52, find the first 4 non-zero terms of the Maclaurin series for the function by multiplying or dividing the appropriate power series. Use the table of power series for elementary functions on page 674. Use a graphing utility to graph the function and its corresponding polynomial approximation. I'm not going to do the graphing. You can do that on your own to see how well this matches up. Be a nice little thing to see, but I don't have that on this computer, so I'm not going to do that. But okay, so we're trying to find the first 4 terms for the power series e to the x times e to the cosine of x. But e to the x is 1 plus x squared over 2 plus x cubed over 6, and so on. And cosine of x is 1 minus x squared over 2 plus x to the 4th over 24, and so on. Make sure that's right. Okay, so sorry about that. I made a mistake. So now I got to start over. So this is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. And then the cosine of x is 1 minus x squared over 2 plus x to the 4th over 24. And so on. We only want, oh, I'm sorry, I forgot the and so on over here. We only want the first 4 terms, right? And so we only want to go up to the 4th power, right? And so the way you multiply polynomials is you multiply all the terms of one times all the terms of the other, right? So the 1 times the 1 will give me 1. The 1 times the minus x squared over 2 will give me minus x squared over 2. And then the 1 times the x squared over 20, x to the 4th over 24 will give me x to the 4th over 24. And I'm done with that. So I move on to the x. I'm done with that because from then on, the powers are going to be bigger than 4, and I only want the first 4 terms, right? Find the first 4 non-zero terms. So then we move on to the x. Multiply all the terms by x. X times 1 is x. X times minus x squared over 2 is minus x cubed over 2. And then x times x to the 4th over 24 is x to the 5th over 24. I don't need that one. That's already too big. Right, so now I'm done with the x and I move on to the x squared over 2. The x squared over 2 times the 1 is x squared over 2. The x squared over 2 times the minus x squared over 2 is minus x to the 4th over 4. And then I'm done with that one. Plus, then I move on to the x to the 3rd over 6. The x to the 3rd over 6 times the 1 is x to the 3rd over 6. And the x to the 3rd over 6 times the minus x squared over 2 is x to the 5th. Don't want that one. I just want the first 4 non-zero terms. So this is approximately, and this is equal to. Now my constant terms, there's only one constant term. That's that one. So we have 1. My linear terms, I have an x, and that's it, plus x. And so I'm done with the 1, and I'm done with the x. Now the x squareds, minus x squared over 2, plus x squared over 2, those go away. And then looks like I'm done with the x squareds. Okay, so now let's move on to the x cubed. And then we have the minus x cubed over 2 plus the x cubed over 6 negative 1/2 plus 1/6 negative 1/3. And so then I get a minus x cubed over 3. Now I need the 4th power. X to the 4th over 24. And minus x to the 4th over 4. And so I have 1 over 24 minus 1 over 4. Negative 5 over 24 minus 5 x to the 4th, all divided by 24. And there we go. All the terms of one times all the terms of the other, but if we continue, we'll get more, we'll get a power higher than these 4, and we only wanted the first 4 non-zero terms. Now I kind of got lucky because they said the first 4 non-zero terms, And technically then I should have stopped at x cubed, but the x squareds went away. And if had I stopped at x cubed, then I wouldn't have had 4 non-zero terms. I would have only had 3. So maybe you want to go a step or two beyond that to make sure that that you don't cancel out some of the ones in the middle. But we're good there. So let's move on. In exercises 55 through 58, verify the sum, then use a graphing utility to approximate the sum with an error of less than 0.0001. Okay, so we're being told here that to verify that this is exactly the sine of 1, right? And so then what we should do is we should recall what is the series, power series for the sine of x. And so the sine of x was an odd function, the summation from n equals 1 to infinity of -1 to the n plus 1. And then we had an x to the 2n plus 1 divided by 2n plus 1 factorial. But we started at 1 and they started at 0. So what we want to do is recognize that to start this 1 behind, this would be the summation from n equals 0, still to infinity. But now we just take 1 away. We took 1 away from this, so we should take 1 away from this, and this should just be -1 to the n, and then x to the, we still need it to be odd, but so that we start with a power of 1, it's 2n minus 1, and on the bottom is going to be the same factorial, so 2n minus 1 factorial. And does that work? Oh no, this was not right. This was 2n minus 1. This was 2n minus 1. That way 2 times 2 is 2 times 1 is 2 minus 1 is 1, right? So this was the same, 2n minus 1. And so then what we need is for this to be a plus 1. These two series are the same. And so then the sine of 1, we just replace the x with 1, and this will be the summation from n equals 0 to infinity of -1 to the n, and then over 2n plus 1 factorial. We just replace the x with 1, and 1 to any power is 1. And so that's the sine of 1. Okay, now then there's this whole approximate the sum. And what I want you to do to approximate the sum is just use the first four non-zero terms. There's some theorems about how many terms you need to be within what limit, and I'm not going to be concerned with that. I'll let your numerical analysis people be concerned with that. So for us, we're just going to use 4 non-zero terms. So then this will be starting at 0, you get 1, and then minus, when n is 1, you get 1 over 3 factorial, which is 6, plus 1 over 8 factorial. No, I'm sorry, 1 over factorial. So that 5 factorial is 120 minus 1 over 7 factorial. 7 times 6 times 5 times 4 times 3 times 2. 5040. And so then you can just punch that into the calculator. 1 minus 1/6 plus 1 over 120 minus 1 over 5040. And this gives us 0.8415. And we can check that with the calculator. This should be pretty close since we went pretty far. The sign of 1 is 0.84147, 0.84146, pretty close. So yeah, rounded off to 4 decimal places, we get the same thing as the calculator. So we did that right. So anytime you're being asked to approximate, just use 4 non-zero terms. Okay. So again, you might be asking why, what's the point of this? Well, we're trying to find the definite integral from 0 to 1 of the cosine of x squared. We can't use the fundamental theorem of calculus because we don't have an antiderivative. Now, we could use the rectangles like we did last semester, but instead what we could do is we could approximate the cosine of x squared with 4 non-zero terms, right? So again, the cosine of x is 1 minus x squared over 2 plus x to the 4th over 4 factorial, which is 24. No, yep, 24. And then minus x to the 6th over 6 factorial, 576. And so then the cosine of x squared, we just replace x with x squared, and we get 1 minus x to the 4th over 2 plus x to the 8th over 24 minus x to the 12th over 576. And so then this definite integral is approximately the same as the integral from 0 to 1 of 1 minus x to the 4th over 2 plus x to the 8th over 24 minus x to the 12th over 576 dx. This is now easy to find the antiderivative of. This is x minus x to the 5th over 10 plus x to the 9th over 9 times 24, 216, minus x to the 13th over 576 times 13, 7488. And then we're evaluating this from 0 to 1. And at 0, of course, we're going to get 0. And at 1, we will get 1 minus 1/10 plus 1 over 216 minus 1 over 7,488. So 1 minus 1/10 plus 1 divided by 216 minus 1 divided by 7408. And you get your approximate area is 0.9045. And there we go. There is your homework for this section.